Hi, welcome back to the channel. If you don't know me, my name is Ryan, and the purpose of my channel is to help you pass the FE Mechanical exam. Today, I'd like to go through the solution to this problem and give you a unique time-saving tip that's going to help you solve this problem in less than 30 seconds. So stick around. We're going to go through the official FE reference manual, find the appropriate references, solve this problem step by step. You can solve this problem alongside me using the first link in the description below, and it also has every other problem that I've solved in my FE exam playlist, all that for free. So go ahead and check it out, refresh those concepts so they'll be ready on test day. I hope you went and solved the problem. Let's get into the solution. It says two identical smooth spheres are moving directly towards each other at a speed of 6 meters per second, just before a head-on collision. If the coefficient of restitution is 1/3, the velocity of each sphere immediately after impact is most nearly. So the first thing I'll get into, just like I promised, is that you can solve this problem in less than 30 seconds. If you recall what the definition of the coefficient of restitution is. Right here, I have this E value, the coefficient of restitution. You can see that the numerator is the difference between the two objects, or the relative velocity after impact. That's what this prime is denoting. Those are speeds after impact. The denominator is also a relative velocity, but there's a negative sign. That's why the 1 and 2 are swapped. And this is the negative of the relative velocity before impact. That's why there's no primes. If we go ahead and write that equation down, that E, which was just 1/3, is equal to the relative velocity after impact divided by the negative of the relative velocity before impact. If the two objects are traveling towards each other, what that's going to mean is that their relative velocity is the sum of the two speeds. That means this difference term right here is going to be 12. If we know that difference, or the relative speed between the two objects before impact, is 12, we can take that 12 and multiply it by 1/3 to get that the difference, the relative velocity after impact, must be equal to 4. What we're given in the answer choices are two different speeds, and there's only one choice where a relative velocity of 4 is present. That's answer choice C. So you can see in pretty much one line, we can get the solution here. Now I'm going to go into the solution in a little bit more depth, but this first equation is still valid, right? That's the coefficient of restitution equation. When two objects collide, we look at it as a system. When we look at it as a system, there's no net impulse. That means that there's another applicable equation called the conservation of linear momentum. That's this top equation here. What it says is that the momentum of the system, the first two terms before the equal sign, that's the total momentum before impact, and the two terms on the right-hand side are the total momentum after impact. And it's saying that they're equal, meaning that momentum is conserved. I just wanted to take 2 minutes here to talk about the first principles of dynamics. A lot of people struggle with retention on the FE exam, and the real truth is that dynamics is very simple. It has some equations related to kinetics, which are these three equations that I'm showing on the left-hand side, and then some equations relating to kinematics, which is just looking at the motion. Because we're dealing with forces and impacts, we're looking at a kinetics problem. These kinematics relations aren't really applicable to us, and we're looking at impact in particular. That's going to mean this impulse momentum principle is going to be important for us. The left-hand side is called impulse, and the right-hand side is called the change in momentum. When you have an impact problem, what's special about it is we use this technique where we want to use the conservation of momentum. Momentum will only be conserved if the change in the momentum is equal to 0. That must mean that the impulsive force has to be equal to 0. When we look at the first ball alone, it's not appropriate to use the conservation of momentum because the second ball is imparting on the first ball a highly impulsive force, a force with a large magnitude applied over a small duration. So it's not appropriate to look at that in terms of the conservation of momentum that's occurring during impact. Same thing for that second ball. The first ball is applying an impulse during collision, so it's not appropriate to look at the conservation of linear momentum. But if we look at that two-ball system, where we have ball 1 and ball 2, before the motion, there's no highly impulsive forces, and during collision, the impulse is self-canceling when we look at this entire system. That means that the total momentum of the system is exactly the same, or the momentum before is equal to the momentum after. M1 V1 plus M2 V2 represents the momentum of that system before, and M1 V1 prime plus M2 V2 prime represents the momentum of the system after the collision. Always think back to the first principles and you won't struggle with retention. Let's get back into that video. If we look at those terms, M1 V1 plus M2 V2, that's equal to M1 V1 prime plus M2 V2 prime. The first thing here is that we don't have a mass, but what we do know is that the spheres are identical. That means that their masses are going to be equal. If their masses are equal, we can get rid of all of these mass terms. What we get is that the sum of the two speeds here is exactly equal to the sum of the speeds after impact. Okay, remember that velocity is a vector, so we pick a positive direction and we have to stick with it. If we have these two objects, objects 1 and objects 2, and they're approaching each other, one is moving with a 6 to the right, the other is moving with a 6 to the left. That means if V1 is positive, V2 must be negative, meaning that these two terms here, their sum is equal to 0. That has to be equal to V1 prime plus V2 prime, plugging into this top equation. What we have is a system of two equations with two unknowns. If we go ahead and solve that system, I'll write down this first equation and the second equation. If we sum these two equations together, the V1 prime crosses out. We get 2V2 prime is equal to 4. 2V2 prime is 4, or V2 prime is just equal to 2. And if V2 prime is equal to 2 and their sum must be equal to 0, that means that V1 prime must be equal to negative 2. Let's go ahead and check our solution here. Okay, so we got the right answer. Just to quickly review what we did, we looked at momentum conservation, which was saying that the total momentum in the system before impact, that was exactly the same as the momentum in the system after impact. So the momentum remained conserved. And from that, we got this first equation here, where the sum of the two velocities after impact was equal to 0. We also had a second equation from that restitution coefficient, which was the second equation now here. Solving those system of equations simultaneously, we were able to find that choice C was the correct answer. Also, if we review what we did on that tip, was all we knew was the relative speed, and we know that we know what the relative velocity is from the choices. It's just the difference of the two speeds. The relative velocity we found was equal to 4 from that restitution coefficient. There's only one answer choice where we have a relative velocity of 4, that's choice C. Using that tip, we're able to solve the problem very quickly. If you found this video helpful, please leave a like and subscribe. It really helps the channel out a lot. Thanks for watching. I'll see you in the next video. Goodbye.